Okay, today our goal is going to be to finish talking about 25 a little bit to see if y'all got any questions on it, and then talk about 26, lhopitals rules. So if you don't have those two things downloaded yet, or the 26, hopefully you've got 25 since we talked about it yesterday. Any of you had a chance or taken a chance to look at any of the 25 homework and have any questions that have arisen from it?
I know.
Yes, ma'am.
Like if you're given S graph,
Uh-huh.
you have to draw S.
Take the derivative of it. Yep. Very good. Good question. I think I have one of those here somewhere. Something like, where is it? I thought I was going forward. This there. Which way am I going? There we go. Okay. So if you've got something like that, for example, this is in your notes. What would be the derivative of this? Well, you need to find out, how do you find the derivative? You look for the slope. What would you tell me about the slope of that line? 0. Where is the slope of that line 0? Everywhere. So how do you signify that it's 0 everywhere? It would just be a horizontal line at x equals 0. So that's what you would get for f prime. Now, what if to begin with, let's take this a different scenario. What if to begin with we had a line something like this? Maybe that's 1, maybe that's 1, and we've got just a line going through that. Okay? What would be the derivative of that? Negative flat value. Can you be a little bit more specific since you know it goes through these 2 points? What could you say? It's going to be negative. I guess the question I'm asking, can you find the slope of that green line? Yes. What's the slope of that green line? Slope is -1. So if the slope of that line is -1, the slope of that line is -1 everywhere. So this is a scenario where you can be exact, and you could draw that the derivative is actually -1 there. So it would be, I'm not going to kill you if you don't put it at -1, but you should be able to do that. Now, what's the second derivative then? Second derivative, now we're kind of back to where we started here with the original problem. The second derivative is going to be 0 everywhere, so you'd want just a horizontal line at the x-axis. Excellent question. If you've got a function, can you always take the derivative enough so that it's eventually going to wind up just being 0? Yes, he says. No, she says. Sine and cosine. Because the derivative of sine is cosine, they're going to flip back and forth. So it's not an absolute. You could say it's always true if what? It's always true. If I took enough derivatives, I'd always get to a derivative that's 0 if what's true? Could you say anything other than sine and cosine? Because the square root of x is going to go what? 1/2.
It's both. If they go opposite negative, it's going to be positive infinity.
Absolute value goes off like that. I don't think it would. Just think about that for a while. I'm not going to answer the question for you now. Can you qualify that functions that all look like this, if I could take enough derivatives that are eventually going to get down to the 75 millionth derivative is going to be 0. There's always a way to get down to 0. Just look at that and see if there's a way for that to ever work out for you there, okay? Yes, ma'am? Can inflection points be critical points? Yes, you can. Yes. I don't think, and I don't have a theorem that proves this, okay? I don't have a theorem that proves this, but I don't think a point can be an inflection point and a critical point. Wait a minute. Wait. Yes, it can. No, I don't think it can. I don't think it can.
25.
Yes.
This would be if the first derivative
Okay?
You have this point here, and it can be a critical point or an inflection point. Is it both?
Yes, it would be both. You would list it. It's a critical point for sure. It's a possible inflection point. Because remember, to be an inflection point, the concavity has to change. Okay? Let's look at a couple of more in this homework, or in this section here. I want to jump over to this graph here. Looks like it's about slide 11. Because this graph is a little bit different than what we've seen before. And the directions are find the derivative, or sketch the graph of the derivative. So how do we always start off to sketch the graph of the derivative if we've got the graph of the function? What do you always look for? Critical points, where the derivative would be 0. Where would the derivative be 0 at in here? Okay, the derivative, it looks like out here, the derivative is getting closer to 0, but it's not. Do you think it's ever going to get completely flat? It's never going to get completely flat, so it's going to be approaching 0. So there are no critical points with this thing. Oh, no. We don't have any critical points. Well, that's good. -4 is an interesting point. Is -4 a critical point? I'm asking the question. It's an endpoint. The derivative is the derivative 0 at -4? Definitely not. What is the derivative at -4? It's undefined. Because look at what your lines are doing here. If we look at the slope at these places, the closer we get back here, what is happening to the slope? It's getting to almost be vertical. So the slope right here at -4 is undefined. The slope is undefined at -4. How do we draw undefined? It's a vertical line. So we've got an undefined slope right there. That tells us that we're going to have an asymptote right there. Okay? We're going to have an asymptote. So we need to draw an asymptote in there. Well, what's happening right next to that? What's happening to the left of -4 on this graph? Nothing, because the graph's not there. So we don't have to worry about that. What's happening to the graph to the right of it over here? It's, talk about right next door. It's what? It's positive. Qualify the positive. Is it really, really positive, or just a little bit positive, or is it really high? Where do you think we should graph this slope that's right along in here at this point? That's right. It's going to start off being way up here, extremely high. And then as we get further and further along, as Mr. West said a while ago, this is getting closer and closer to 0, right? But we agreed it never gets to 0. So what does that graph look like then? It looks kind of like a sideways U, right? Something like that. Now, does it come down like that? Or does it do something like come straight down and like that? I'm not too worried about how exact you get in there. We don't have enough data to tell the exactness there. But we know that the graph is going to look something like this right here for it, okay? So that's what the first derivative looks like. Can anybody conjecture what the second derivative might look like? Second derivative is talking about the derivative of the green line. So what can you tell me about the derivative of the green line? -3, -2? Yeah. Yeah, and in either case, we can't draw it exact. Because in either case, it's not getting flat here. Do you think this ever gets to a place where the derivative is just the same thing? It's always getting closer and closer to 0. So we can't really draw exactly what this looks like. This thing is always getting closer and closer to the x-axis, so it's never flat. We don't have any critical points in this green line. We don't have any. So that tells us that it's either always positive or always negative. What do you think it is? Always positive or always negative? What is the slope of this red line, slope of this green line? It's negative. Does it start off being negative infinity or 0? Starting right in here, what would you say? How would you describe this here? Is it a large or small number in magnitude? Way up here. Very large. So we're going to start off being somewhere down here. And what happens the further along the x-axis we go? It gets closer and closer to 0. So what does the second derivative look like? Second derivative looks something like this. The third's just going to flip back up there. The fourth's going to flip back. Fifth, flip, boom, 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 boom. We're just going to keep flipping back and forth, back and forth, back and forth. Each time it's going to move slightly, but it's going to be very hard to see that just in a sketch. Okay? So the main thing I wanted you to see here is this vertical asymptote. And the asymptote, we got an asymptote out of that because the slope was undefined. So anytime you're trying to sketch a graph, if the slope is undefined, that means there's going to be a vertical asymptote in your derivative there. Okay, let's look at one or two other problems here. There's a couple like this in your homework. Does that scare you? Sketch the graph. I don't know. See if you can sketch a graph that meets all of those criteria. It doesn't have to look like your next door neighbors. It may look slightly different. But the graph must have all of those criteria. There's not one single right answer. I'd start off by doing the first line and putting what I know to be there. F of 2 is equal to F of 4 is equal to 0. So boom, we've got two x-intercepts. All right. The second line says that the derivative is less than 0 if x is less than 3. What does that mean? Now, we're trying to graph f, okay? We're graphing f, not f prime. We're graphing f. So, if we're graphing f now, what does the fact that the derivative is less than 0 mean? It's going to be a negative slope. So, the slope is going to be less than 0 if x is less than 3. What does that mean about the function? The function's going down. So, we know that here's 3 right here. The function's got to be going down until it gets to 3. So it either does this. Would you agree that that's going down? Or it could do this. And might go even further down. But it's got to do either the blue or the green. Would you agree with that? We don't know which yet based on that, but it could do either one of those. I bet very few of you drew something that looked like the blue line. Most of you probably did something that looks like the green because that's kind of what we would normally think of there. So let's look at this next statement here. F prime at 3 does not exist. Right. We just talked about it. It doesn't. So that means that there must be an asymptote right here. All right? So now, does that help you decide if it looks like the green or the blue? Probably the blue. It could do what the green is doing still, couldn't it? It could just come right there and stop. I mean, we've had graphs before they come to a point and stop. But I think it's probably going to be the blue. But let's don't erase the green just yet, okay? The first derivative is greater than 0 if x is greater than 3. What does that mean? It's going to be increasing. The function is going to be going up. So the function's either going up like that, or the function is going up like that. Either the green or the blue. Does that make sense? All right, now the last thing says the second derivative is less than 0 everywhere except 3. Does that help you? What does that tell you?
The blue.
Has to be the blue, because the second derivative tells us what? It's concaves down. Concave up would tell us that it holds water. The green looks like it might hold water, so the green's not going to be right. We're going to get rid of it in both cases. So our graph should look something like that, we think. Is that hard? But do you see, these are the type things that I want you to get to where you can do. Think about what the words mean. Think about how you transport it into graphs and all, because this is a big part of understanding calculus, is being able to see it visually as well as algebraically. All right, I'm going to stop boring you with all of this fun stuff, because you can do. I think you should be comfortable with that. I want us to jump over to 26. And I know all of you are going to be excited about this, because you see the first fun. Look at this lovely face Miss Mary Martin's making. She's just so happy to see these. Why is everybody so happy to see these? What is that? It's a what? It's a limit. We haven't looked at limits since September. Why are we bringing these ugly animals up again? Well, what are limits? How do we evaluate a limit? Can't graph this thing. First thing you're going to do is what? Plug it in. All right. So we plug in 0. What's e to the 0? Anybody know? 1. And 1 minus 1 is 0. 0 over 0. What does that tell us? Indeterminate. That means we can't do our happy dance because we don't know the answer. So what do we have to do when we get indeterminate form? We've got to use some type of algebra from here. And how do we use algebra? Well, we need to factor something. We need to rationalize a numerator. We might even use trig. None of that's going to work when we've got a lovely e in there. I mean, that's not going to factor any way that's going to help us, because it won't allow us to cancel anything out there. So now we would normally be stuck with what then, if we can't graph this thing? We could graph it and maybe get some idea from that. What's the other thing that we could do? Anybody remember? Plug in numbers around it. So we could come in here and say, well, if I put 0.001 in there, what's e to that power? And we don't really have any idea what that is either. So we're really kind of stuck at this point. But a long time ago, a lovely Frenchman with the last name of L'Hôpital came up with something, and he proved something called L'Hôpital's rule. And L'Hôpital's rule is on the next slide. I want to see if you can read that, all that mathanese there, and explain to me what L'Hôpital's rule says. The hospital rule, yes. Yes. It kind of looks like hospital, but the correct French pronunciation is lhopitals. This is an ingenious little thing. And if y'all can figure it out, I'll let you use it. Chase is nodding his head, said, yes, we're going to figure this out, people. So whenever somebody wants to explain it to us, explain away.
I understand the epivaxes, but what's the geovax? The bottom. One of it.
So isn't it just the derivative of the original on top and bottom?
Yes. L'Hopital's rule says if you've got a function that looks like this, we've got a function on the top and a function on the bottom. We've got a fraction. If we can't find the derivative, or by that I mean if we get the indeterminate form 0 over 0, if you can take the derivative of the numerator and the derivative of the denominator and take that derivative, then you'll have the same answer. So we don't have to go through, suddenly this is a game changer for us, people. A huge game changer. We don't have to go through any factoring. We don't have to go through any trig identities or any multiplying by the conjugates and all that. Suddenly, all we have to be able to do is take the derivative of the numerator, the derivative of the denominator, and evaluate that limit. Okay? So let's go back. We can't evaluate this like it is. What is the derivative of the numerator? E to the 2x. What's the derivative of e to the 2x? You don't have to take the ln to take a derivative. Right. The derivative of e to something is e to that same something times the derivative of that something. Okay? So e to the 2x times 2. What's the derivative of the bottom? 1. And as soon as you see the 1 down there, you should do your happy dance. Why? We know we can evaluate it now. Now, once we get to this point, now we can just evaluate it by plugging and chugging. If we put 0 in, e to the 0 is still 1, and 1 times 2 is 2, and 2 divided by 1 is 2, and happy dance, we just solved the problem. That's the limit. Okay? Now, that's much easier than what we were doing back in September, isn't it? Yes. Like that, don't you? This works anytime it's in indeterminate form. Notice this bottom part down here. Any of these qualify as indeterminate form as well. So if you've got infinity over infinity, negative infinity over infinity, infinity over negative infinity, anything that's not a number, you should be able to use L'Hopital's rule on. If you get a number when you try to evaluate it, that's the answer anyway, so you just stop. So we kind of reduced evaluating limits down to 2 things. Plug in. If you get a number, great. If you don't get a number, take the derivative and go at it again. Where did the 2 come from? Because when we take the derivative of this, the derivative of e to a power is e to that power times the derivative of the argument. The derivative of 2x is the number 2. You with me? Anytime we take a derivative, e to the 2x, yes, sir? Yes, because this tells us that it's not going to be, it's going to be approaching the number 2. You're right. So we would expect this to be something that goes like this. That's what we would expect to see out of that. That's right. It does what now? When you graph it? Let me see. E to the 2x minus 1. All right, but now remember, we are looking at this at 0, aren't we? E to the 2x minus 1. That's intriguing. Everybody, if you look at his graph, what would you say the limit should be based on his graph there? Looks like it's two different numbers. It looks like it does not exist. So have we messed up?
I was thinking once you take the limit of the bottom one.
Well, but there's nothing to plug in. The limit of 1 is just 1.
I mean the derivative of the bottom.
That's taking the derivative again, though. Did we mess up here, people?
We don't take the derivative twice.
We didn't take the derivative twice. If this had been 0 over 0, we could take the derivative again. But it's not. So did we? The question is, let me graph it up here and let's see. Did we? The question on the floor is, did we mess up, people? Let me graph it up here. F of x equals e raised to the 2x minus 1. All of that needs to be in a parentheses. Divided by x. Oh, my graph looks different than your graph. What was your graph again?
Maybe this way you put it into the calculator.
Oh,
Maybe that's the only way.
yeah, put that and let's see what happens there. Okay? Okay, so the graph, looking at the graph, you would think that it's 2. I had me worried there. Looking at the math here, we come up with it being 2 there, okay? All right, that worked. Okay, scared me there for a second.
I still don't get why we get 2 from this.
From this here?
Yeah.
Because we're taking, how do we take the derivative of e to the 2x? If you go back and look at your sheet, the derivative of e to any power is e to that same power, but we have to use chain rule, times the derivative of 2x. The derivative of 2x is just the number 2. So that's how we got this quantity right here in the blue. Now we're evaluating it at 0. When we put 0 in for x, e to the 0 power is 1, times that 2 is 2. Okay? Connor, does that answer your question now on the 2?
Yeah, I forgot how to do eliminate it. I didn't plug in the 0.
Oh, you didn't plug the 0 in. Okay, yeah. Yeah, we've got to plug that back in. So let's take this new information and see what you can do with solving that problem there. First of all, plug in. Now, plugging in infinity is kind of hard. I understand that. But if you plug infinity in, I think you get infinity over infinity. So use lhopitals. Which is something that you can figure out. You're smart people by now in life. And while you're doing that, I'm going to graph this thing. Okay. So when we plug it in, we get infinity over infinity. What's the derivative of ln of x? 1 over x. So we can change this to limit as x approaches infinity of 1 over x over 1, which just becomes the limit as x approaches infinity of 1 over x. Now, what do you get when you evaluate that? We've got a 1 in there, so we know we're going to get an answer out of it. What's 1 over a really big number? A really small number, which is the number 0. So we would think that the limit is going to be the number 0. Does our graph support that? Does it look like it's getting a little bit closer every time? I mean, we can keep doing this forever if we really wanted to, but it's getting closer, so it looks like the graph goes up and then it comes back down. Very good. Very good. Do you like this? This is almost fun, isn't it? The limit as x approaches negative infinity of x squared e to the negative x. See what you come up with when you try to figure that out. Don't forget to plug in. Remember back to when we first had talked about the limits. I said the thing you're going to forget to do is plug in and evaluate. Always plug it in first. Because if you plug in first and then get an answer, that's the answer. You can't, L'Hopital's rule doesn't work if you get an answer out of the limit, okay? So when you plug in, do you get infinity over infinity? Because that'll become e to the positive x, which is infinity. So when we take the derivative, we get the limit as x approaches negative infinity. Ooh, that was ugly. Of 2x over negative e to the negative x. Because the derivative of negative x is negative 1. What do we get there if we plug in now? If we plug negative infinity in, we get negative infinity over negative infinity still. Well, what do we need to do then? No. We need to go a derivative again. Because if that had given you 1, then it would have given you 1 back here also. So we still get the same thing. When we tried to evaluate this first one, we got infinity over infinity. When we evaluate the derivatives, we got negative infinity over negative infinity. That's still indeterminate form. So take the derivative again. What's the derivative again? Well, the derivative of the numerator becomes 2. Now we can do our happy dance. We know we're not going to get infinity in the top now. If we take the derivative of the bottom, we get negative e to the negative x times another negative, which would make it positive. So we get 2 over e to the negative x, right? So now when we plug it in, we get 2 over e to the negative infinity, which is really e to the infinity, which is a really big number. And 2 over that really big number gives us 0. So you can continue taking derivatives as many times as you need to in order to evaluate functions, the limits of functions like this. Second, third, fourth, fifth, sixth, however many you might need to do. I would not expect you to have to take more than 1 or 2. Looking at this next slide here. Yes, looking at this slide. The limit as x approaches infinity of e to the negative x over root x. Can we use L'Hopital? L'Hopital said we needed a fraction. Right. As this is written, we can't use L'Hopital's rule. But we can rewrite it. Yes, ma'am? Good question. She asked a question that I should have asked. Do we even need L'Hopital's rule? What happens when I put infinity into this thing here to begin with? I get e to the negative infinity, which is a really small number, and I get infinity, which is a really large number. We can't really say those two things cancel each other out, because we've learned, at least we've discussed in here before, that there's different infinities, right? Y'all remember that? Yes. That, if you take infinity, what happens if you subtract infinity from infinity? You get infinity, okay? So we have to be careful with that. So we need to make it L'Hopital's rule. Now, once we make it L'Hopital's rule, still won't work. So what's the derivative of the numerator? 1/2 x to the negative 1/2 over, what's the derivative of e to the x? E to the x. All right? Switch what? Yes, you could switch them. You could. Will it help? Not really. But I like your thinking there, because there's something you do want to do here. Because if I plug it in now, I don't know what I get. I need to do something with this x to the negative 1/2. Now, the best thing for you to do right now is to simplify this to 1/2 over e to the x, the square root of x. Okay? Now, how did I make that a square root of x in the denominator? Right, the x to the negative 1/2 came down. Now, I'm kind of excited about that because I've got a 1/2 in the numerator, so I can solve this problem now, I know. Very good question. Could I put the 2 in the denominator as well? I could. I chose not to, but I could go ahead and make this, if I wanted to, the limit as x approaches infinity, 1 over 2 e to the x root x. Either way, we should get the same answer. What's e to the infinity going to be? What kind of a number? Really big number. And the square root of infinity is going to be a really big number. It's smaller than infinity, but not much. And when we multiply infinity times something, it's going to be a big number. So we're getting back to 0 again for the derivative. If we had left the 1/2 in the numerator, we'd have still gotten there. All right. All in all, I don't think this qualifies as very difficult, does it? All right. When we plug this in, we get 0 over 0. Now, most of the time, this was the easy problems we did before, because you look at this and your mind goes to algebra and says, I can factor the numerator, so I'm going to factor the numerator and cancel out. And that's fine still to do. But L'Hopital's rule will still work here, people. So if we use L'Hopital's rule, then this becomes 2x minus 2 in the numerator and 1 in the denominator. And suddenly, we can do 2 times 3 is 6 minus 2 is 4 all in our head. Had you gone ahead and done this the old way, you would have factored it as x minus 3 and x plus 1. And then the x minus 3's would cancel, and you'd evaluate it by putting the 3 in, and you'd still get to 4. So either way, you're going to wind up with the same answer there. All right, people, I'm not going to go through this problem, but again, what would be the logical thing for you to do here? Before we talked about L'Hopital's rule, how would you solve this before L'Hopital? You plug it in, and when you plug it in, you get 0 over 0. And you could try and factor this thing if you wanted to. Yeah, that's what I would do. I'd just turn my nose up at it. I wouldn't do it. How would I get rid of that square root? Anybody remember algebraically how to get rid of that square? Multiply by the conjugate of it. So we could do this. This is the old way. This is not L'Hopital's. And it'll work. And to be honest with you, if I'm sitting here and I've got to take the derivative of a square root with an x squared on the inside, if my algebra skills are better, I might be better off doing this the old way. Because taking the derivative of this numerator, it becomes 1 over that thing times negative 2x. There's places for me to make mistakes in there. So it's okay for you to do it the algebra way, but it's also okay for you to do it L'Hopital's way. I don't care which method you choose there. It does not matter to me in the end. You should wind up getting a nice answer out of it. What mistake can you see that students probably make in using L'Hopital's rule? What? Forget to plug it in. Yes, they plug in it. Forget to plug a number in to begin with. That's a common mistake. Anybody see other common mistakes that students might make with this? Obviously, you can mess up taking the derivative of something. A common mistake that students would make here is to look at this and see quotient and think quotient rule. Using L'Hopital's rule, you don't have to use quotient rule. You take the derivative of the numerator and put it on the top, the derivative of the denominator and put it on the bottom. That's all you have to do. But a common mistake would be to use quotient rule here. So don't use the quotient rule. Just take the derivative, e to the x minus -1 over 1. And then you're going to put in the 0, and you're going to get 2. It looks like 1 plus 1 is 2. Don't use the quotient rule there. Now, you got to use quotient rule everywhere else in life, but not here. Any questions about L'Hopital? Congratulations. You have suffered through the first half of AP Calculus. There are no more lectures. There are no more lectures until January, okay? You've got homework 25 due tonight. You've got homework 26 due tomorrow night. You've got 2 FRQs due Friday. You've got WebAssign Monday, a little test on Wednesday, 2 FRQs the next Friday, and a little exam the week after that. Okay? So the rest of your time is going to be for you to use in class as you see fit, getting things accomplished.